Okay, so let's get started. First of all, I would like to just go over homework 5. As usual, whenever I grade the homework, I give you the comments, the common mistakes that people made on that homework. So basically, the first common mistake was the gross error. Basically, we find that word, gross error. Remember where when we talked about gross error? What does it mean, gross error?
A huge
No, actually, it's just human error, okay, in measurement. So basically, some people, for example, when they try to measure the peak-to-peak voltage here, they just basically ignored these very small areas. They are very clear, actually. Basically, they are like one of these marks here. And each one of these marks actually is like 0.2. So basically, they ignored one from here and one from there. So they ignored 0.4. Which is really big. I mean, I usually, when I take measurements, when I look at answers for a problem like this, basically I can ignore plus minus 0.1, but I cannot ignore 0.2. 0.2 will be wrong because basically it's very clear that it's 0.2. Okay, so for example, if you measure this to be 0.2 or 0.1 or 0.3, that would be okay. If you measure it as 0, then this would be wrong. Okay. So this was made here and almost on all problems. Okay, please try to measure as accurately as you can. Okay, so basically this is the allowable error. Beyond that, you will get deduction. Okay, this is the first mistake. This is a gross error because it's a human error, if you remember. Okay. The second mistake people made, the second most common mistake, was the scale. Some people just ignore that scale altogether, okay? For some reason, people use the scale for the time axis correctly, but the scale for the voltage axis or the vertical axis was usually incorrect for some reason. I'm not sure why, okay? So basically, so many answers were actually measured correctly as centimeters, but actually the answer was not multiplied by the correct scale from here. So the second problem was the scale, okay? This was very common mistake.
So doctor, times
yes.
40 times 10 minus 2?
No, where is 10 minus 2? Where can you see the 10 minus 2?
Because centimeter.
This is centimeter here. This is centimeter here.
Yeah, so just leave it as it is 40.
Yes.
Okay.
I mean, this is the usual. This is what you have on the scope. So basically, this is centimeter and this is centimeter.
Yes.
Each one of these marks is a 0.2 centimeter. Okay?
Okay.
So this was a very big mistake. So you can imagine that this would be a per meter. So basically, this would be a meter or something. This is not a meter. I mean, this is actually a centimeter on the scope screen itself. Okay?
Yes, okay.
Okay. So let me clear all here. The other problem actually was basically in the phase, in the part where you calculate the phase. This is a very common mistake also. So basically for the phase problem here, some people computed the delay, okay? The delay between these 2 points. Basically, I told you before that the phase will be like if you take a particular point in the waveform, in the first waveform and the second waveform, basically you measure the distance between them. So for example, I can take this point and that point. I can also take, for example, this point and that point. There are 2 points exactly in phase with each other. So this is the starting point of the waveform. And this is a starting point of the other waveform, so you can compute the distance between them. So basically, we measure this time delay, okay? So assume that this time delay was like tau, okay? How can we compute? I asked you for the phase difference. I didn't ask you for the time delay. So basically, I expect the phase difference to be as an angle, not as time, basically, okay? So how can you compute the angle, the phase angle from the time delay? How can you do that? It's a very simple actually. You should have learned about that actually in 250.
You divide the time delay by the period and then multiply.
Yes, right. Basically, each period corresponds to twice pi, right? So basically, if you have a certain tau, it should correspond to what? So basically, you basically get tau over the period times twice pi, and you get your phase difference, okay? You can put here twice pi, or you can put here 360 degrees, whatever. They are both okay. Whoever put it like this or like that, it's fine, okay? So basically here, you measure the time delay, and basically you know that the period, you already computed the period to compute the frequency. So you already have the period, okay? So basically tau over period equals to basically twice pi over the phase delay that you want to estimate, okay? So basically you can basically make the phase delay as basically just from this. I think there's, yes, this is just it, okay? Over period times twice pi, okay? No, so there's actually, it should be the other way around, okay? So let me just, so basically it should be phi over twice pi. So basically phi should be equal to the time delay that you measured over the period times twice pi. And this, the result will be in radian, okay? If you want to have it in degrees, then you put it as 360. Both are fine, both are okay, both are correct solutions, okay? One less common error was that when I asked for the RMS value, some people just took the peak-to-peak voltage and multiplied that by 0.707, or basically it's 1 over square root of 2, basically this value right here. But actually, what you should have is just V peak. So basically here, you should have only the V peak, which is V peak to peak over 2, okay? This was a very small mistake, but actually, some people, actually a few people actually did it wrong that way. Are these issues clear?
Yes.
Okay. So let's go back and finish the part we talked about in the resistance. We finished all the way right before the temperature coefficient of resistance. What we are going to talk about here is the effect of temperature on the resistance. Usually when you're talking about a linear resistor, a common type of resistance, like all the resistors that we see in nature, not the nonlinear ones that we talked about, like the LDR or the thermistor, we talk about a regular resistance. Basically, the resistance of all pure metals increase with increasing the temperature. So basically you have a linear increase of your resistance with temperature. And of course, you have this change actually, is dependent on the delta temperature. So basically you will have a temperature coefficient of resistance. It's called like alpha. And this alpha actually is basically 1 over degree centigrade. And we talked about it last time. And basically, since we're talking about the delta temperature, it doesn't matter if it's 1 over degree Kelvin or 1 over degree centigrade, because it's a delta temperature. So it's not going to matter. Okay. So the equation to do that, so if you want to describe a linear curve like this, you're going to find that the equation basically looks like this. Basically, theta here is the temperature, okay? The temperature relative to a certain degree, basically. For example, if you have alpha 0 here, this is a temperature coefficient of resistance at 0 degrees centigrade, meaning that this theta right there should be relative to 0, okay? If I have it relative to, if I have alpha 20, for example, if I have the temperature coefficient of resistance at 20 degrees, then I should have theta minus 20. So depending on which one of them, which temperature coefficient resistance, the reference temperature for the alpha I actually can use this equation or that equation. Of course, if you have, for example, if you have two resistances, if you have the same resistance at two different temperatures, then if you divide these two together, maybe I can show it to you clear here. Maybe I can write it in another. Basically, if we talk about, if I have, for example, alpha, if I have alpha 0, okay, meaning that everything is relative to 0, okay, then the resistance at temperature, for example, 20 degrees, okay, will be equal to R naught 1 plus alpha 0 times 20. If I want to measure or want to calculate R at 30 degrees, then it's going to be like R0, R at 0, 1 plus alpha 0, 30. If I divide these two equations, basically you're going to get rid of this from both sides. So basically it's like R at 20 relative to R at 30 is equal to 1 plus alpha 0 times 20, 1 plus alpha 0 at 30. Okay? If you took it in a general form, basically this 20 here will just be basically put this as T1, okay, or theta 1, because he's using theta here, and this is theta 2. And basically this will be R theta 1, and this will be R theta 2. Okay, this can be very handy if you're given the resistance at a particular temperature, not at 0, and you want to measure the resistance at another temperature. For example, if I gave you R, if I told you that a particular resistance was equal to, for example, 100 ohms at 20 degrees, and I want you to measure R at 30 degrees. How can you do that? And of course, you're given alpha naught, and you're given alpha 0, okay? And basically, you want to measure R at 30 degrees. One solution is basically to apply the equation, the original equation, which is going to be like 100 ohms, which is R at 20 degrees, is equal to R0 times 1 plus alpha 0 times 20. Okay, and from this equation, you have this, you have this, you have this, you can compute R0. And then you apply this equation again. R at 30 is equal to R0, which you computed from there, times 1 plus alpha 0 times 30. You can do it this way. But it's much easier to do it this way. Because here, basically, if you know that this is 20 and this is 30, this is equal to 100, which is the resistance at 20, over R30. You can compute it in a single step. Okay, it's up to you. Both of them are okay, but this seems a little bit easier. Is that clear?
Yes.
Yes.
Okay. So just make sure that if you do that, basically you do that relative to the correct temperature. Basically, if you have alpha 20, if you're given alpha 20, not alpha 0, you have to use the reference temperature as 20, not as 0. Okay. Let me try to give you an example about that, but let me give you an example, short example. Basically, let's go back to the. Basically, if you talk about, if you're given alpha 20 was given like, for example, 0.0001, for example, okay, for a certain resistance, okay? And basically you're given R at 30 degrees is equal to 100 ohms. And you want to get R at 50 degrees, okay? How can you do that? First of all, you have to have everything referenced to R20. So the equation here now will be R in general at any temperature will be equal to R20, not R0 at this time, 1 plus alpha 20 theta minus 20, like that. Okay, so the changes here was the changes here are here and basically in the reference temperature there. So if I want to use the relative temperature equation like the R1 over R2 and so on, I can do it like this: R over of theta 1 over R over theta 2 is equal to R20 will be a common factor between the two, 1 plus alpha 20 theta 1 minus 20, okay, over 1 plus alpha 20 theta 2 minus 20, minus 20 also, okay? So just be sure to use the reference temperature, the correct reference temperature that you're given from this temperature coefficient of resistance, okay? So if I'm given alpha 0, then everything is relative to 0. If I'm given alpha 20, then everything is relative to 20, okay? And this will apply here and there. Is that clear?
Yes.
Okay. So of course, the temperature coefficient of resistance, you have to actually either have this table or be given that value in the exam, okay? I usually get you that value or put that value in the problem itself. So basically, you don't have to worry about carrying that table if you don't want to, okay? Just I want to point out something that might look a little bit strange to you. See here, he actually groups each 3 digits together. So basically, as you see it here, like this is 0.003 space 81, okay? Can you see that? It's actually common in all of them. This is just like 0.00381. There's no difference. It's basically just a matter of convenience for writing the numbers. It's not going to affect anything. So basically, the space here, as if it's not there. So don't worry about having a space between these two parts of the same number. Okay? Can you see the mouse, by the way?
Yes.
Okay. So basically, that's what I'm talking about. Don't worry about the space here in the middle. Okay? It's as if it's not there.
So, doctor, I can say 0.00381 or?
Yes, it is like that. It is exactly like that for all of them. Okay, it's just a matter of convenience. Some people actually, or some textbooks actually use that convention in writing numbers. They just group each 3 numbers together. At least the first 3 numbers in the decimal digits, they group them together, and basically the rest, if they are more than 3, then they will group another 3, and then the rest will be by themselves. They put space between each 3 numbers. Okay?
Okay.
Okay, so basically this is a very important issue actually, because usually the temperature rise is one of the major factors that determine the rating of electrical appliances. Basically, if you have a certain insulation in your electrical appliance, you're usually afraid that at a certain point, the temperature of the conductor or the resistance, usually any cable will be essentially a resistance. You're afraid of that the temperature will be high enough to melt the insulation. If it melts the insulation, then you might end up having a short circuit or a big problem. Basically, sometimes you can actually start a fire because of the high temperature of the regenerated from the resistors. So basically, you have to really be sure that your temperature is under control. So basically the rating, the power rating of electrical appliances is actually related to the maximum temperature that you can actually withstand in that particular electrical appliance. Okay, so for example, if I buy like a distributed or basically electrical distribution unit, like basically if you take from the AC outlet, basically, and take that into like 3 different devices, okay? Usually the cable that goes from the AC mains to the distribution of power to 3 different appliances, usually it is rated to a certain current. If you go beyond that current, if you try to basically get more current from that device, you will end up usually having that insulation. The insulation of that cable will basically melt, and basically you will end up having a short circuit. And if you have a circuit breaker at home, it might actually go off. It's a big problem. So basically you have to make sure that basically you get a particular, if you want to get transfer the electricity to a particular device, you make sure that the cable is rated for the current that you will need for that particular device. Yeah, any questions? Any questions?
No.
Okay, so basically this is one of the very important things. One of the things that you might want to look at, basically regarding that, but this is actually not included in the course, but let me give you an idea about it. Basically, if you're talking about the size of the cable or the thickness of the cable, the diameter of the cable, there is something called gauge. This is basically spelled as gauge. Okay. Basically, this is the standard for American wires. I'm not actually, I don't remember what this stands for, but this is like a scale basically. And basically, this scale here determines the size of the cable itself, the diameter of the cable. So they tell you that, for example, you have gauge 2, for example, or gauge 1, or gauge 3, or gauge 5, or gauge 0.5, or whatever. So basically, there's an equation. For example, if you can go to a website, I actually encourage you all to do that. Maybe I can make it one of the first bonus questions. You can go to a website and basically supply the current. And you can supply also the length of the cable that you need, the length of the cable that you, or the basic, if you want to connect electricity between 2 different, basically from AC mains to a particular device. So you supply the length and you supply some other geometric things. And basically it would tell you which gauge would be suitable for your application. So it gives you directly which gauge that you can order and use for your application. Okay, so this is very important. For example, if you work in a certain place and you want to connect electricity from one place to another, you have to make sure that you basically buy the cable of the correct size. Otherwise, you'll end up having a lot of problems. Okay, so basically this, I will put this as the first, this would be the first bonus question. I will ask you to basically go visit one of these sites, and basically I'll give you some parameters. I'll ask you to go to these sites and basically compute which gauge would be the right gauge for this cable. I'm sorry, this is a cable. Okay, cable. Okay. So basically, this will be a bonus question that I will post today, inshallah, on the website. Okay. You can submit it anytime from now until the very end of class, right before the final exams. Okay.
Okay.
Okay. So let's take some exercises here, some examples. Here, a coil of copper wire has a resistance of 200 ohms when its mean temperature is 0 degrees centigrade. Calculate the resistance of the coil when its mean temperature is 80. This should be very simple, actually. How can we do that? How can we solve that problem?
Just
R at 80 is equal to, here actually, you're talking about the mean temperature. You started with 0 degrees centigrade, and actually what you have here, he relies on the table that we saw before, the table that we just saw before, the table that had the temperature, the alpha 0. So basically you have here alpha 0. So basically this will be equal to alpha 0, R0, 1 plus alpha 0 times 80. Okay, because this is 80 minus 0. R0 is given. This is R0. Alpha 0 is from the table. It's also given. So basically just plug in the numbers and get the value that you need from this. That's it. So this is just a direct substitution in this equation. Is that clear? That problem clear?
Yes.
Yes.
It's a very straightforward problem. Okay. This other problem, when a potential difference of 10 volts is applied to a coil of copper wire of mean temperature of 20, this is the mean temperature, the current of 1 ampere flows. Okay, so basically you have a voltage and you have a current. So basically the resistance at 20, you can compute it from this voltage over that current. Okay, so R20, let's just keep putting the information together, be equal to 10 volts over 1 ampere, which is 10 ohms. This is R20. After some time, the current falls to 0.95 ampere, yet the supply voltage remains unaltered. So basically, when I have a resistance, when I have a current flowing through a resistance for some time, what should happen there? What would happen there? I have a current I have a resistance R. What happens there?
The resistance.
Basically, we have a power dissipation of I square R, right? And this power dissipation will go in the form of heat, right? Can you understand that? If you have a resistor, if you have a current flowing through a resistor, after a while, it's gonna raise its temperature, right? The temperature will be higher because basically you're dissipating power in that resistance, and this dissipation is in the form of heat. So when this drops to 0.95, then basically the new R will be what? Will be 10 volts over 0.95 amperes, right? This is the new R. What he needs to know is what is the theta at that time. So basically, theta at 20 was like this, was given like this. Theta, or the resistance at the theta, at unknown theta, was given also like this. So basically, you can use R20 over R theta will be equal to 1 plus alpha 0 times 20 over 1 plus alpha 0 times theta. And you have this, you have this, you have this, you have this already. So basically the only thing that is missing is theta. So the idea here is after a while, the temperature of the resistance will be higher, will be a little bit higher due to the flow of current. As long as you're flowing current in the resistance, there will be power dissipation that is equal to I square R. This I square R, the power dissipation, will basically go to heat the resistance. When you heat the resistance, given that the voltage applied on the resistance is exactly the same, this means that the current, after a while, will be a little bit less, because basically the resistance will be a little bit higher because of the higher temperature. Is that clear?
Yes, doctor.
Okay. So basically, this is one sort of questions actually that you will see a lot. Actually, you will see in the homework, you will see in the final exam. This is a very important kind of problem that you need to actually understand very well.
Doctor, can you give us the final result of this examples?
For this example, actually, this is an example from the textbook. So basically, you find the final answer. You find the solution actually in the textbook. So you don't have to get the final answer from me. It's right there. Okay, so this whole problem actually is one of the examples in the chapter. The chapter I think it's chapter maybe 4 or something. I'll let you know just a second. It's actually chapter 3, chapter 3, right? Okay. So basically, section 3.6 to 3.8, you'll probably find the parts that are related to this particular problem there. Okay.
Okay, thank you.
Let's see what's in the homework 6 that is related to that. You'll find more examples of this. Okay. So in homework 6, can you see homework 6 now?
Yes.
Okay, let me start by problem 3. In problem 3, you have several types of resistors, one with six bands, one with 5, one with 4, and one with 3 bands. And you have 3 types of surface-mounted devices, okay? All of them are resistors. You're asked here to estimate the resistance values of each one of these components, okay? Basically, in that particular problem, all you have to do is just go back and look at this particular page. Okay, you will see that the 6 bands are there. The 5 bands will be basically without the last one, without the temperature coefficient. Just everything is exactly the same. The 4 bands will just remove the one of the digits here. So basically, we're going to have 2 digits times the multiplier and the tolerance. The 3 digits will be just the basically ignore the tolerance. If you don't have any band for the tolerance, you assume that it's 20%, as we said last time. Okay, so basically this is just like an exercise for you to use that particular color code and basically get the values of each one of the resistors that are in these pictures. Would that be a problem?
No.
And of course, if you have codes like this in the surface-mounted devices, what we said last time is that basically for the 3-number code, it's exactly the same as the 3-number code or the 3 bands here in the resistors. So basically, you have 22 times 10 to the power 3. That's it. If you have it like 4, like this is actually going to be like 3 times 10 to the power 2. Okay, so basically you have the first 3 digits times 10 to the power 2 here. If you have it like this is the code that we talked about, like with R and K and M. This will be what? Can you remember which value of a resistance is that? When we have R?
4.7.
4.7 ohm, right? That's correct. Okay, so this should be straightforward. By the way, the submission of this homework will be after the exam. So basically, I give you like 2-3 days after the exam so that you have enough time to solve it. So you can focus on your exam next Saturday. Okay, so this is due, I think, on Tuesday. So basically, you have plenty of time to work on it. Okay. Here you have, this is a mixture of different things here. Actually, this is very simple. You have a coil consisting of 2,000 turns. And basically, they have cross-section of 0.8 millimeters square. Let me annotate that as well. So basically, you have 2,000 turns. Okay. And you have a cross-section area of 0.8 millimeters square. The length per turn is 80 centimeters. The resistivity is given like this. So basically, for each turn, you can compute the resistance as what? Rho L over A.
Yes.
And remember the equation. Rho is right there. This is rho. L is basically the 80 centimeters. A is basically the 0.8 millimeters square. But you have to be very careful with the units. Convert everything to SI before you do anything. So basically, this would be what? Let's convert everything to SI. You have 0.02 times what? This is supposed to be ohm meter.
10 to the minus
meter.
6.
This is micro. So, right, you have to multiply by 10 to the minus 6. L is 80 centimeters. Give it 80 centimeters. Should we leave
10
that?
to the minus 2.
2.
Right.
Two.
Right.
Multiplied by 2000.
You have here 0.8
10 power minus 3.
minus 3. This is
Minus
square,
6.
millimeter square. This is a
Minus
common
6.
mistake. Yes. The millimeter is 10 to the minus 3 meter, but you have here millimeter squared. So basically, you have to put it like this. And basically, that's it. So this is more like a problem of basically units, just the SI units, just making sure that the values, all the values are in SI units. So here he's asking for the resistance, which is whatever we computed here, and then he's asking for the power dissipated if it's connected across 110 volt DC. So basically the power here will be what? Will be like V squared over R, right? Because this is what you have. This is power, PR. Okay. So basically you have V here and you have R from this equation here, and that's it.
Doctor?
Yes.
Do we multiply the resistance we get by 2000?
Yes, right. You're right. This is for one term. That's right, bro. That's right. So basically here, this is the resistance for one term. You have to multiply this resistance by 2000 turns in order for you to get the resistance of the whole coil. Okay, that's right. Okay. Thank you for catching that. You have any questions about this problem? In any case, we're going to have, inshallah, on next Sunday, it's going to be after the exam. If you want to have any question, if you have any questions about this homework, we're going to go over it again on Sunday, okay? If you have any questions on Sunday, right before you submit it on Tuesday, I'll be happy to answer your questions next week. But the questions here, as you will see, actually, they are much easier than the questions that you saw before in the other parts. So basically, you shouldn't really worry about, you're probably going to be solving these questions without any difficulty, inshallah. Here, it's a very simple, the second one here is a very simple problem. It's very similar to the problem that we just saw. We're talking about the windings of a DC motor. Basically, when he talks about a DC motor or whatever application, basically it's exactly the same. You're talking about a resistance at the end, okay? So basically, the field winding is just a resistance connected directly across 440 volts supply. The windings were at room temperature at 17 degrees centigrade. And basically, the current at that time was like 2.3 amperes. So basically, R17 is equal to what? 40 over 2.3 amperes. So you have that. After the machine has been running for some hours, as just like any other motor, whenever we run a motor for a while, when you touch it, you find that it's hotter now. It's warm. It's getting warm. Okay. This is because of the dissipation, the heat dissipation in the resistance of the windings. So basically, the current changed from 2.3 amperes to become 1.9 amperes after a while. Okay, the voltage is exactly the same. So again, here you have R theta is equal to 440 over 1.9. This is the new resistance at the higher temperature. What he needs you to compute is basically the temperature throughout the winding, assuming that the temperature coefficient resistance of copper is this value right there. So again, we're going to do exactly like we did before. R theta over R17 will be equal to 1 plus alpha 0, because this is given at 0 here. This is alpha 0 times 17. Times theta. This is unknown. Over 1 plus alpha 0 times 17. You have this, you have this, you have alpha 0, you have 17 here. So basically the only unknown here is the theta, and you can compute from this equation. See that it's exactly the same problem. It's in different wordings, but it's exactly the same problem. It's exactly the same problem, okay? Can you see that?
Yeah.
Okay. So any questions about that? Okay, so basically, if you have any questions, we still have time after the exam. So basically, feel free to ask me again about it, okay? If you have any question about this particular homework. Okay, now I'm going to start with the part about the capacitors. I'm going to talk a little bit about the capacitors. I'm going to show you a video that you will probably like. It's not a very nice thing to do yourself, but actually sometimes it's nice to watch. Actually, it's very dangerous situation. But I just wanted you to just to be sure not to be in the same situation. Okay, because the use of inductors carry a little bit of risk. So basically, the capacitor or condenser, sometimes people call it condenser, is a device which can store electric energy. Okay, it's basically any capacitor, let me just put it like this. If you have any two conductors, if this is a conductor and this is a conductor, and you have a dielectric in the middle, okay, this is a capacitor. Okay, so for example, if you have a resistance, okay, like this, okay, and these two leads are in front of each other like this, this will carry actually, this will have a straight capacitance between these two conductors. So any two conductors with a dielectric in the middle will constitute a capacitor essentially. Okay, of course, you basically the capacitor has the ability to carry or to store some charges on these plates, on the plates of the capacitor itself. And as we will see, actually, this will carry an energy, and this energy can be actually cooled from the capacitor and be used in some application. Okay, so the essential construction of a capacitor is just two conductors with a dielectric in the middle. Usually, when you have something that is that simple, the capacitance will be extremely small. So in order for you to be able to get a reasonable value for the capacitor, or a large value if you want to, what you need to do is basically create a very large surface area. Just make the two conductors as large as possible, and basically make the area facing each other as large as possible. So this is usually done by basically having something that looks like this. Basically, you have like foil, aluminum foil, and you have dielectric in the middle, and the other one here you will have another aluminum foil, and basically you have here also a dielectric, and basically you wind that so that you have a surface area that basically is much larger than basically the volume of the capacitor. Instead of having the surface area just basically expanded, basically you try to fold it, you make it a little bit small in size so that you can use it, and basically the physical dimensions of it will be as small as possible. We'll explain that in a little while. Maybe I'll talk about the technologies to explain things a little bit better. So basically the graphical symbols for capacitors are like this. Basically you have a fixed capacitor will be like this. Usually you have, sometimes you have a non-electrolytic, or basically a capacitor without polarity. Without polarity meaning that if you connect your device this way, or you basically make the connection the opposite way, it's not going to matter. Okay, for the electrolytic capacitor or any capacitor type which has a polarity, it's very important to observe that polarity. Otherwise, you might end up having an accident in the lab, okay, or whatever that happens. Okay, I'll show you in a short while how that happens. There is a very special type of capacitor called varactor. Basically, varactor is a variable capacitance that varies with, basically use an electronic manner to change the value of the capacitance. There is another way to create a variable capacitance with a mechanical variable capacitor. We will see the difference between these two. But for now, we just know the symbol of the capacitor. If it's like this, then it's basically, it doesn't have polarity. It doesn't have a positive and negative terminals. Basically, you can connect it any way you want, which is very much like what you used in the lab, like the ceramic capacitor that you use in the lab. They don't have any polarity. If they have polarity like this, you have to really observe that. Otherwise, it's going to be a really big problem. We're going to start again with the code for the capacitors. basically the standard values of the capacitors are not as clear cut as they are in the resistors. So basically it depends on the technology of the capacitor or what's made of. If it's a ceramic capacitor, if it's a mica capacitor, if it's a paper capacitor, if it's a electrolytic capacitor, if it's a tantalum capacitor, each one of these has several values, but they are not really, they depend also on the company basically that produces the capacitor. So you'll have really a wide range of values, but there is no real rule to basically apply like the one that you had for the E12 series or the E48 series or the thing that we saw in the resistance. So if you want to choose a particular value for a capacitance in your circuit, if you're designing a circuit and you need a particular value for the capacitance, or you need to know the available values, I would suggest that you go to something like DigiKey and look at the values there and basically select based on the technology, based on the polarity, based on the whatever, the price, and basically select from the values that are available under these constraints. You have also a code. The code is really very common. This code actually can be used to know the value of the capacitance. So if you have a ceramic capacitance, the ceramic capacitance usually has a number in the middle, which is a 104, okay? This 104 works exactly the same as the resistance, like 10 times 10 to the power 4. But here it's not going to be in farads, it's going to be in picofarad. Okay, so basically here it's going to be 10 times 10 to the power 4 picofarad, which is going to be what? 10 to the power 5 picofarad, which is going to be 0.1 microfarad. Okay. If you have an electrolytic capacitor, sometimes of capacitor, not just electrolytic capacitors, actually, they have the whole information written right there in front of you. So basically, they will have the information like 10 microfarad written very clearly like this. And you have also the voltage, the maximum voltage that it can take. Basically, this is the tolerance or the rated voltage for the capacitor. And because this is a capacitor that has polarity, there should be a way to designate the negative or the positive terminals. Usually, for the electrolytic capacitor, you have the negative leads. As you see here, you have negative, negative, negative. This is actually designation for the negative leads of the capacitor. So basically, this is the negative lead of the capacitor. For the other parts of the code, if you have 3 lines like this, the first line actually is for the maximum voltage. So if you have 2E, for example, you look it up from here, 2E is basically 250 volts. If it's 1H, then it's 50 volts, and so on. The third line here is a tolerance. K here is about, if you have K here, for example, it's plus minus 10%. Usually, if you don't have any information about the tolerance, it's usually plus minus 20%. Okay? So basically assume that it's plus minus 20% if you don't have any designation for the tolerance. Okay? Let's see some examples. How about this one? Can you read the value of this one here?
22 multiplied by 10 to the power 4.
Yes. Picofarad.
Why picofarad, doctor?
Basically, this is the convention that people use. Okay. So basically, it's 22 times 10 to the power 4, which is what? 0.22 microfarad. Yes. Right?
Yeah.
0.10 to the power 4 or 10 to minus?
This is to the power 4, to the power 4, right? Basically, this is picofarad, meaning that it's multiplied by 10 to minus 12. So basically, okay. I took this here and make this 6, and basically make it micro here.
Yeah, it's a picofarad.
Yes, it's picofarad. Basically, the code here is basically 22 times 10 to the power 4 picofarad multiplied by this. Okay. How about this? You have 500 what?
Picofarad.
Picofarad, right. It's not very difficult, by the way.
Picofarad.
Picofarad, everything is picofarad, unless it's otherwise specified, like this, for example.
22 micro.
This is written right there. So basically, whenever it's written like this also, see here?
Yes. Yes.
Written very clearly, okay? When it's written like this, then there's no doubt about it, okay? This is just the regular value. Whatever is written is the one that you use. Here, actually, the 20 here is the rated voltage. And this is the rated voltage. This is the voltage rating for this capacitor. And actually, here also, this is the anode. This is the plus part of the, this is basically the plus terminal of this capacitor. This has polarity also. This doesn't have polarity, and this doesn't have polarity. Basically, you can connect it any way you want. This one and this one don't have polarity. The other ones have polarity. See here, this actually is the positive terminal. Here you have the negative. See the negative here. So this is the negative terminal here, and this is the positive terminal here. See here, this is what?
20
what?
picofarad.
2.2. Unless otherwise specified, it's picofarad. Okay, and this is 25 volts, and this is the positive, and this is the negative. Sometimes actually you can find capacitors with axial leads. Remember the axial and radial, if you remember from last time. Axial meaning that you have a cylinder and basically the leads are running on the axis of the cylinder. So basically sometimes it's very difficult to know which one is the negative and which one is the positive. Which one is the negative here and which one is the positive?
The negative is on the
The
right.
right one. The right one.
Right. Why?
Because
Because
there's an arrow.
You have like an arrow, yes. Basically, it's made to make sense. They use things that make sense so that it's very difficult to make problem or basically make a mistake about it. Okay, so basically, if you make a mistake about it, if you actually go beyond that rated voltage, or if you connect the capacitor in the opposite polarity, you will find, you'll find soon enough that it's a big problem. It can cause a big problem because basically such capacitor can actually explode. Okay, I actually edited some videos from YouTube that I wanted to show you. Okay, just to basically give you an idea how dangerous using a capacitor in the opposite polarity or with a voltage that is higher than the rated voltage. Can you see the video now?
Yes.
Yes.
Okay, let's watch together. Okay. Can you see that? This is a tantalum capacitor. This is like the one in the right to the bottom of the screen that we saw before. See how it went on fire?
Wow.
Let me show you the other ones. The electrolytic capacitors actually are much more dangerous because actually they explode like a bullet, like as if you were having a gun and basically triggered that gun. But see now? It's extremely dangerous, okay? If you're around one of these, when it's exploding, it can be really dangerous for you. So please make sure that you know the rated voltage before you use a capacitor with polarity. Basically, you observe the polarity and you observe the maximum voltage for that particular capacitor. This is another example, actually. Here he's going to put that particular capacitor with opposite polarity, and see what's going to happen to that. He actually put it inside a bottle so that he doesn't get hurt. So see what's going to happen now? Actually started to burn. He actually is going to plug it in now. Okay, you'll find that it's beginning to become black, and all of a sudden it's going to explode. So it's extremely dangerous. So please, whenever you're using a capacitor in your circuit, be very careful when you are connecting that capacitor. Okay, it's not a joke. Okay, when this happens, when this explosion happens, it's not going to be a very nice thing to have around. Okay, you can destroy your instruments. You can actually hurt yourself or the people around you. Okay, so make sure when you're using a capacitor with polarity, or when you have a rated voltage for the capacitor and you're using something that is basically close to that rated voltage, you should be really very careful. Usually, if you have in your circuit, if you have like 100 volts I would suggest to use 3 times that much for the rated voltage of the capacitor that you're going to use. So for example, if I have 100 volts in my circuit, if the maximum voltage in my circuit is 100 volts, at least a 300 volt capacitor should be used, not less than that. Okay, you don't want to be like with 120, for example. No, because actually the rating is usually on the average, basically on the average of the production run. So sometimes some capacitors are weaker than others. So it's better to be safer than basically than being right at exactly at the edge of the specification where something can go wrong. Okay, so be sure when you're using a capacitor to make sure that you know the polarity first. If you even if you're using a very low voltage, if you use the opposite polarity, it's going to explode. Okay, if you have 5 volts and you put the capacitor on the opposite polarity, it's going to explode, believe me. Okay, I'm telling you that because it happened to me. Okay, so basically you make mistakes and basically learn from them, but actually it's not a good thing to try this just to know exactly what's going to happen. It's not really a very nice thing to have. Okay,
Doctor, even
yes.
if it was a high voltage capacitor, if I may.
No, actually it was just a regular capacitor. It was like 25 volts rating, and basically if you put it in the opposite direction, it's not made to basically pass current in the opposite direction. So when you do that, basically the chemicals inside are just going to explode, basically. Okay. Because you're passing current in the opposite direction. It's not made to pass current in the opposite direction. And this can be a problem. Okay. I'm talking about the DC voltage, by the way. If you're talking about AC is different because actually it's going up and down. It's not a big deal. It's not a problem. But actually, if you have something like a DC voltage that is higher than the rated voltage or applied in the opposite polarity, then this will be a big problem. Okay. When something like that explodes on a printed circuit board, it can ruin the printed circuit board itself. Because as I told you before, usually the printed circuit boards are multi-layer printed circuit boards. If this explosion destroys some of the tracks in the inner layers, then there is no way you can actually repair the printed circuit board. So you should really be very careful. If you for example, repairing a particular printed circuit board and you're replacing a capacitor, if you put it in the opposite direction, this will be a big problem. Okay, just be very careful about that.
Okay.
Yes.
When I can use ceramic capacitor and when I can use electrolytic.
Actually, it depends on the application you want. For electrolytic capacitors, actually you have much larger values. So here, for example, you have 47 microfarads. Here you have 0.22 microfarads. Okay, so usually ceramic capacitors have much smaller values than chemical capacitors or electrolytic capacitors. So it depends on the kind of application that you have. Okay.
Okay.
If you go to somewhere like DigiKey and you want to order a capacitor, then there is a list of specification that you will find. Including the capacitance itself, the value of the capacitance, the technology, like as I told you before, we have several types. We have, for example, we have the ceramic capacitors that you usually use. Probably you use that a lot in the lab and probably that one also as well. Sometimes you will see that one, but actually it's not that common as these two, but actually it's very common as well. So this is a ceramic capacitor. This is a mica capacitor. This is an electrolytic capacitor. This is surface mounted. I'm not sure exactly what the technology was, but I think it's called metal film capacitor. This is a tantalum capacitor. There are several types, and each one of them has certain advantages and disadvantages. Sometimes it's a price, sometimes it's a particular application, sometimes it's like the parasitic effects that are present inside. Sometimes it's the kind of capacitance value you can get from these technologies. Sometimes it's the maximum voltage, the rated voltage. Sometimes you need the capacitors with a rated voltage of a few kilovolts, for example. Sometimes you can get it from particular types of capacitors, not the others. Okay, so I think this you'll get a feel of something like that when you try to design a certain application for a certain application, and you look for a capacitance. You will find that the range of capacitance values that you need are in a particular technology, not in the other technologies. Okay, sometimes it's the size. You can actually miniaturize, make the size very small for some technologies. The others cannot. One type of capacitor is called a paper capacitor, which is basically like two aluminum foils with a paper, just like a sheet of paper in the middle, in between them. And this actually can get some capacitors made out of that, but they are really very small in capacitance, and they are usually large in size. But they are very stable and they are very cheap. So basically, they can make up for the for some application they can be used, but in others they cannot. The package also is very important. Like what we saw here, you can have through hole, you can have surface mounted. The same thing we talk about in the resistance. The polarity, some technologies have polarity, some others don't have polarity. So basically, you can choose if you want to have a polarity for your capacitance or not. And basically, this is one of the specifications you choose in a particular capacitor. Of course, the tolerance. Usually, the tolerances here in the capacitors are much larger than those in the resistors. So plus minus 20% is usual, basically. Plus minus 10 or 55% are usually very high in price. They are not really as common as the plus minus 20%. Of course, we talked about the working voltage. And basically, there is also a temperature coefficient for the capacitance. It's not as critical as the resistance because usually it's affected only by the room temperature. It's not like the resistance where the resistance itself creates temperature. Or basically, if you use it a lot, it's going to have a higher temperature after a while. No, it's not like that here. It's just a matter of the temperature coefficient relative to the ambient temperature. So if I use it in a room that has air conditioning with 20 degrees centigrade temperature, it's going to be a little bit different from using it outside, like in the summer here in Jeddah with the temperatures like 40. Okay, a little bit of difference. It's a slight difference, but it's not that big of a difference. There is something called also DC leakage. DC leakage, we're going to talk about it at the end of the lecture, but not this lecture, probably inshallah next lecture. The parasitic effects also are present here in the capacitors. These are related to the DC leakage because actually there's a leakage resistance here in the capacitor, which actually makes sense. It's basically if you have if you charge a capacitor and leave it for a while, it's basically going to lose temperature. It's going to lose the voltage, even if you don't basically take any current from it, because basically the insulation, as we talked about before, it's not 100% insulator. It has very, very, very large resistance. But this very large resistance with time is going to pass enough current to discharge the capacitor. So basically you have a leakage resistance here. Sometimes you have of course your basic capacitance. Sometimes you have a resistance from the leads themselves. And sometimes you have an inductance because also of the leads, the kind of leads that you're using. So basically, it has a model that looks like this. But usually, if you work in close to DC with a very low frequency, you basically see mostly the capacitance. Okay, but just be informed that there might be some other parasitic effects or some side effects to the capacitance that you have to take care of or have to consider. Okay. I don't want to get into equations this lecture. I'm going to show you an interesting application so that you can at least understand basically why we are talking about capacitance. Have you heard about defibrillator? جهاز صدمات بتاع القلب.
Yeah.
Have you heard about it?
ايوه سمعت.
It's very common if you watch any hospital TV series on TV. You probably see that 100 times, something like that. So basically, you have these paddles, and basically you charge or at least operate this device, and basically discharge them on the patient so that you can get some. Basically, if you have some abnormal heartbeats like this, you can actually, if you put an electric shock, you basically return back to the regular ECG or the regular cardiac rhythm. Okay, so basically this device is just based on a capacitor. Basically, it has a capacitor that looks like this actually. See how much capacitance? 32 microfarads. Okay, and the voltage, the withstanding voltage here is what? 6K
6K?
DC, 6K volts, 6,000 volts. This is why basically when you're trying to apply this to a heart, usually the standard values for the energy you want to discharge on the patient's heart is like 360 joules. Okay, so basically you have to apply a shock of 360 joules. And as we know, as we will know, actually probably heard about it before in the circuits course, the energy stored in a capacitor is 1/2 CV squared. Have you heard about this equation?
Yeah.
Yes.
So basically, if you put this as 32 microfarads and compute the voltage here, you will find that the voltage that you need to have on the capacitance in order for it to store this much energy is about 4,743 volts. So here actually you see that you have a little bit higher, like almost more than 1,000 volts higher withstanding voltage or rated voltage, so that you can actually store that voltage without any problems. So basically this whole device is based on just being having a capacitor like this. You have a capacitor and all the device does is basically charge this capacitor. That's it. And all you do to apply or to use this capacitor is just basically apply it on the patient. So basically you apply this here and this here, or this here and that here. For example, this, no, one of these and one of these, basically. One of these and one of these. This one and this one here. If you do that, then basically the current will flow in the patient's heart, or this one and that one, you can flow on the other side. So basically you apply the energy that is here on the heart in the form of a current. One very important thing I want to at least give you an idea about here regarding this capacitor. This capacitor here can be charged with like almost 5,000 volts, okay? If you happen to be a biomedical engineer, if you work as a biomedical engineer later, for those of you who are in the biomedical program, if you're trying to repair one of these devices, be very sure that this capacitor is discharged before you touch it, okay? Because if you touch it, actually, it can actually electrocute you, okay? This voltage, even if it's a DC voltage, if you touch it, basically, if you make a complete circuit, you know, with this particular capacitor charged to 5,000 volts, basically, you can have a big problem, okay? So basically, even though the capacitance might be actually, sometimes you actually leave the device. Actually, this device should be charged at all times because this is an emergency device. You don't want to have to wait for the capacitor to charge while the patient is having a heart attack, okay? You want to treat the patient as soon as possible. So basically, this should be plugged in at all times. So the capacitor is usually charged at all times. So when you're trying to basically repair that particular capacitor, replace it, or repair any part of the machine, you have to actually, there's usually a way for each one of these devices to discharge the capacitor. So you have to do that, and you have to actually measure the voltage across the capacitor terminals before you touch anything inside the machine. Otherwise, it's going to be a really big problem. There are other applications, by the way, where you use capacitors to store thousands of volts, and in each of them, it's exactly the same. Regardless if it's a DC voltage, some people think DC is not dangerous. Actually, DC can be very dangerous when the voltage is high enough, okay? Because it can pass the current that is dangerous enough to cause harm into the human heart, or basically in the human body. It can sometimes actually cause burns in the human body. So just keep that application in mind, and basically keep that safety tip in mind, okay? Each capacitor, you have to make sure that it's discharged before you try to work with it or touch its terminals, okay? Okay, so do you have any questions? So as we agreed last time, inshallah, on Wednesday, we're going to have a mock exam or a practice exam. I actually thought about having the exam at 4:30 instead of 9:30. Would that be a problem? Because actually 4:30 should be, you will end at about 6. Okay, it should be a little bit early, because some people actually don't like to work at night. So how about
Great.
Yeah.
so the
Good.
practice exam will be on Wednesday at 4:30. Would that be okay?
Yeah.
Okay.
Doctor,
Yes.
can I submission homework by today?
Homework what?
Homework 5.
If you
Yes,
didn't
today.
submit it, please submit it
Because
today.
I forget.
Yes, please submit it today.
Yes, thank you.
Okay, no problem. So basically, the exam itself, as we agreed last time, is going to be on Saturday from 9 to 10:30. The regular time for the exam was like 1 hour, 15 minutes. Okay, I added another 15 minutes just in case, you know, the how you're going to solve the problems and upload them and things of that sort might take you a little bit more time. And usually, if you use a different system of exams, usually you're kind of sometimes there is a confusion there. So basically, I added 15 minutes to just make sure that this will not affect you. Okay. If anything happens during the exam that may actually affect your performance, just let me know. Okay. We will deal with it after the exam. Okay. Unfortunately, during the exam, there is no way we can communicate. So basically, the exam will be there. It's going to start exactly at 9 automatically. Okay. On Blackboard. It's going to end at 10:30. Then you can actually, after that, you can send me any emails you want, okay? You can let me know any issues that you have. Usually in the exam, no questions are allowed during the exam because a part of the exam is for you to understand the problems. So if you have any questions about whether you understood the questions right or whatever, or if you want to ask about anything, just ask me after the exam. Okay?
Okay.
So next time, next Saturday, next Tuesday, inshallah, we're going to continue with the capacitors. And on Thursday, we're going to have a review lecture where we can actually go and explain anything of the previous lectures. We can actually go over can actually explain the lectures again if you want, or I can solve any practice problem that you want. Okay, so just be prepared because basically I'm going to come and ask you for questions. What you want me to explain or what you want me to solve for you. Okay?
Okay.
The mock exam, the practice exam will just be made of basically homework problems. And I might use some problems from the midterm exam of last year. Last term, okay? But it's not going to be, it's basically not going to be a new, we don't expect all the problems to be new. For the actual exam, usually all the problems are new. Okay, I don't repeat the questions again. I don't repeat, for example, homework questions. I don't repeat them. Okay, you might have the same idea. Of course, it's going to be the same idea. The same idea is basically all problems actually might have different wording, but usually have the same idea like the problem we just solved. You know, about the temperature variation of DC motor windings. But basically, the wording will never be the same. So basically, don't rely on the questions on the homework. Don't expect questions from the homework to come exactly the same way in the exam. Okay? Also, if you, next time, if you have any questions about the exam or about any part of the exam, you can start with questions from you before we continue with the capacitor. Okay?
Okay.
So next time, if you have questions, ask me next time at the beginning of the lecture.
Okay. Doctor,
Okay. Were you able to find the recorded lecture on the website? On the Blackboard? The recorded lecture from last time. Have you seen that?
Not yet.
Actually, it's you'll find something called recorded lectures, right below the lectures. Okay, on the Blackboard menu. Okay, okay, so it's on the left. You find recorded lectures. So you find a link to the lecture of last time, and gonna also post or upload the lecture from this time. So whenever we have an online lecture, it's going to be posted as recorded lecture. The things that we solve together on the notepad here, I'm going to also post there. Okay, so whenever we solve something on the notepad, I'm going to post it there as notes. Okay, so that you can have these notes actually if you want to take a look at them again. Okay.
Thank you, Doctor.
So good luck, inshallah, with your preparation for the exam. And please let me know if you have any questions, okay?
Okay.
Okay. Okay, shukran. Thank you. See you, inshallah, on Tuesday.